I was wondering, if you could keep on, please.
Greetings, Algebra 2 students, especially to the students in my ACE College Algebra 2 class at Avon High School. Purpose of this video is to finish up our discussion over section 15.1. I'm going to back up with this document here so that you can kind of see where we've been up to this point. Course 15.1 started to talk about the introduction of the logarithm, just basically giving you a brief overview of what logarithms are used for and the fact that a logarithm is just really nothing more than an exponent. And we sort of segued into kind of introducing this idea of the natural base e, but didn't really go very far with it. So this is where I'm going to start with, and we're just going to talk about this number e for just a moment. And then the video will end with this final example in your notes here on page 4 that will just basically discuss how you can solve very simple logarithm equations that contain a single logarithm in the equation, both with bases of really anything, 9, 3, and 25, but we'll also talk about this natural logarithm. So before we do that, I'm going to back up to page 3, and we're going to talk about this number e. So it says, considering this expression, 1 plus 1 over n to the n, we are wanting to complete this table for the given values of n. Now, in order to do this, we are going to use a graphing calculator technology. The calculator that we use happens to be the TI Inspire. And any particular scientific calculator will be able to do this with a certain degree of efficiency. But if you use the TI Inspire, by using a list in a spreadsheet, which sort of looks like a mini Excel program, we're going to be able to compute this rather quickly. So to get things started, I'm going to let the A column represent my independent variable n. I'm going to put that in the very top row where I could just basically name variables. Now, the second column, I'm going to use the second row because this is certainly a formula. And the formula is clearly 1 plus, and then I'll generate a fraction here, 1 divided by n. Now you can see that I'm down here. And the fact that n is bold, it just simply means that I have something entered into n previously that it's going to be picking up. And then I'm going to raise that to the n power. Now when I hit enter, we're going to get some kind of a conflict detection message. It's just basically saying, hey, we've already seen an n in this problem. Are you wanting to carry this out? And what we want to do is say yes. We're going to go ahead and use a variable reference because n is a variable. It's basically the value that we're inputting into this particular function. So once I do that and hit OK, I should be able to start filling in this chart. If I let n equal 1, as we can see from the table, you can see we're just going to basically add a 0 each time. I get a value of 2. Okay, well, they want us to keep going with that. So if I let n be 10, something weird's going to happen. It's going to be a little deceptive because you're going to look at the 10 input and think the output is this very large number, but the TI Inspire CAS version is a pretty smart cookie. It's converting this to a fairly nice, did I call this a nice fraction? Well, it's a fraction. Maybe it's not a nice fraction, but it is converting it to as an exact value as best as it can. So I'm going to outsmart the calculator, and on the input of this 10, if I place a decimal there, I will be sure that I will get decimal output, which is going to be a little bit easier for us to read. So it's interesting. We've moved from 2 to 2.59. Let's continue to do this by adding a 0 each time, but again, making sure that there's a decimal. We'll just keep going and and see where this takes us. We're up to 100,000. Now I'm going to add a million, which is 6 zeros. And the document had us stopping at 10 million. It's interesting that they use scientific notation for one and not the other. But in any event, we have a very interesting result. It seems like our decimal value is sort of converging upon this 2.71828 perhaps, and we would still be getting more accurate with future decimal places. Of course, we only see 5 places right now in our table. And that really is the crux of this particular situation. What we have discovered, and I'm just going to write the final decimal that I got right here, 2.71828. And I want to kind of make it known that this does continue. It is an irrational number. And that is this value that we call E. Um, it it's much like pi in that it doesn't look like a number. It is attributed to a Swiss mathematician named Leonhard Euler. Obviously, his name starts with the letter E, so that's how this particular number was coined, sometime after its discovery at least. And that's really what we have in this blank here. As n approaches infinity, the value of 1 plus 1 over n to the n will be this E. And it's got this very important role in mathematics as it is referred to as the natural base. We're going to talk about that even more so in some future videos. So if we end up wanting to use this very strange number as a base, well, I suppose that it's somewhat accurate to say log base E of A, but that's a little unusual. You're not going to see that. You're not going to encounter that very much in mathematics. So instead, we're going to use this kind of notation, ln of A, which means the same thing. This means the natural logarithm. Now, it might seem a little peculiar that the L and the N are backwards. Doesn't natural come before logarithm? Should this be NL? Well, you have to kind of understand that the birth of this particular concept of mathematics certainly took place in Europe, not just with Euler, who was a Swiss mathematician, but with some other prominent French mathematicians, one of which was Napier. And in these Romance languages in Europe, oftentimes the adjective will follow the noun. So thus we have logarithm naturale in this case. Now, in a previous video, I think we discussed how you could use virtually any calculator to compute these logarithm expressions that have bases that aren't so pretty like 10. So if you're going to figure out, well, what is the log base 3 of 20? Well, as we said before, in this particular calculator model, if I could move over to a scratch pad, I have a button that says I can use a base of 3. And I'm going to put a decimal there to get decimal output. Right? But the problem with most calculators, especially scientific calculators, is that you don't have that luxury. So what you would have to do instead is use a common logarithm of base 10 and then put the argument in the numerator and then put the base, which in this case is 3, in the denominator, and you would find that you get the exact same answer. Now, this particular document that I'm working with here, in fact, I'll go ahead and write this answer, 2.72683. There is no connection between the fact that this is pretty close to E. That's just a coincidence. But this particular document will also say that you can do that same division if you use natural logarithms. So if you don't want to hit your log button on the calculator, you could hit the ln button as well, and you would find out that you would get the same exact result. It's the change of base formula. And I'm going to spare you the agony of showing you how that would work for these other two examples, but indeed it would. And it asks, what can you conclude about the values of the log base b of a, and both of these ratios, and the fact is all three of these are equivalent. But as I said before, if you have a calculator that's very sophisticated and will compute logarithms of any base, this change of base formula idea does become a little bit obsolete. All right, now for the finale of this particular video, we're going to run through a few of these examples here, these equations, and kind of discuss how this is going to be done. But before I do that, I want to kind of take you on this little journey, and I'm going to create a new page to do that. Because I often equate the solution of logarithm equations to kind of living in a world where we have these two islands. So I have this island, and this island is called Logarithm Island. I know, this is a little crazy, but bear with me. So we have Logarithm Island, and on Logarithm Island, there lives lots of logarithms. And across the sea, across this raging sea here, with the waves crashing about, right, we have Exponential Island. And on Exponential Island, as you can probably imagine, there lives lots of exponential expressions. That would be expressions that have powers that are x's, variables. But fortunately for us, there happens to be a bridge that connects the two islands, because nobody, and I mean nobody, wants to tread across these shark-infested waters. So we'll go across the bridge. And in order to go across the bridge, we just simply take a logarithm equation, which might look like this. Log of any base, b, of, let's say, some x that's equal to a. And then on the exponential island, we would rewrite this as the base b to the power of a, because after all, logarithms are just exponents, and that would be equivalent to x. So there's a bridge that connects these two equations, much like there's a bridge that connects the two islands. So that's kind of the philosophy that I want my students to keep in mind as they're working with logarithm equations. So I'm going to snip something here so that we can use it, if the calculator or if the software will let me. And let's take a snip of our little equation, send it to the clipboard, and then if I go back here and unlock, maybe, there we go, and if I paste this giant equation here, I'm going to shrink this down just a little bit, and I'm going to put this here at the top, and let's see if I can lock this back in. Might want to move this over so that we can actually read the instructions. There we go. So if we want to find the value of x in each of these logarithm equations by rewriting the equations as an exponential equation, then we are going to want to cross this bridge. So we have the log equation here where the base is 9, the argument is x, and the value is negative 2/3. We could write this as the base 9. Notice we're right here. The base is 9. We would raise to the a power, which in this case is the negative 2/3 power. And of course, that result is x. And essentially, you have just solved this equation. You haven't simplified it, but you've solved it. And if we want to continue with this, we would see that, well, the negative exponent just really means that we could rewrite this by placing the base into the denominator. And this does not have a pretty answer because we have the cube root of 9 squared in the denominator, which could be thought of as the cube root of 81 is equal to x. And we could leave it like that. I don't have a big problem with that. We don't focus a lot on simplifying square roots. My personal opinion, it's overrated. But just truth be told, this will simplify if, let's say, a multiple choice question mandated that. So we could break the denominator into the cube root of 27 times the cube root of 3, which would give us 1 over 3 cube root of 3. And then I'm not going to rationalize this. I'm going to keep this just as it is. Okay? We can do the same thing for natural log equations. So for example B, we have to keep in mind that the base is now e. There's like an invisible e right there. So if I cross the bridge, I have e to the third equal to x. And the good news about that, we are done, because you can't really do much with e to the third power. I don't really care that we type that into the calculator. Of course, we could, and the calculator will give us some kind of, let's make sure that I type the right thing in here. We could type in e to the third, make sure I put a decimal there, and yeah, I get something a little bit bigger than 20, but that's not important to me. I'm going to go ahead and leave this in terms of e for right now. In example C, something again very similar. Base is 3, exponent is -3, and we set this equal to the argument. Now we just solve this, as this would be 1/27th equaling to 2x plus 1. You subtract 1 over from the other side. 1/27th minus 1 is equal to 2x. So you'd have, 26 over 27 is equal to 2x. So that would mean that x would be 26 over 54, or that would reduce to 13/27ths. Now I'm going to go ahead and pause the video, and I would like for you to practice your skill in crossing this bridge and rewriting these logarithm expressions as exponential for D, E, and F, and then you can check your answers with me in just a moment. All right, welcome back. And as you can see, I've gone ahead and solved D, E, and F, well, at least as much as I think I could at this point. So let's kind of walk through part D of this example. We would cross the bridge and find that we get 25 raised to the x is equivalent to 5 square root of 5. Now from this point here, we're fortunate in that we could change some bases here to make everything sort of equivalent at 5. So the 25 would be 5 squared, still raised to the x, which is eventually 5 to the 2x. Over here, I thought to take 5 and raise it to the 1/2 power so that I can add the two exponents to get 5 to the 3/2. And now that my bases are the same, I can just equate the exponents to each other and easily solve for x to get 3/4. Let's jump down to f before we look at e. With f, very similar situation except with the natural log. I would take e to the 5th, which is equivalent to x plus 3, and then really the only thing I can do is subtract 3 over, and I've isolated x, and thus I've essentially solved the equation. Now when you look at e, your first thought might be to cross that bridge and take 2, which is the base, raise it to the x plus 2 power, and of course that gives you 9. But the problem with this is that there is really no nice exponent of 2 that's going to give us 9. So sometimes when you do this change of base formula, you kind of find yourself still with this very difficult task of getting the x by itself. So we can't really be very, pedantic about this. We can't be like little robots that just always wants to cross that bridge. Because the fact of the matter is, we were perfectly fine staying in logarithm world or on logarithm island, because your goal in this problem is one thing and one thing only, and that's solve for x. So that can be accomplished by simply subtracting 2 over to the other side. And you could leave your answer like this. There's nothing wrong if a student said, okay, well, I want a little bit more definitive decimal type of answer. So you could type in the log base 2 of 9 and subtract 2, and the answer is 1.169. But that's really something that we don't have to do. It might seem very, very elementary just to subtract 2 and be done with it. But for right now, that's perfectly fine with me because you've just presented this x in the most accurate way that you could. So I hope this helps out just a little bit. I know that there's quite a bit more to talk about with our journey into the world of logarithms. I have a video that covers section 15.2 that goes into the properties of logarithms, which will allow students to kind of expand their knowledge on the topic. And there's so many things, so many wonderful things that you can do with these in both mathematics and science. So I hope this video helped, and I will see you next time.